Today we're going to be continuing in Chapter 6, looking at normal probability distributions. I'd like to start with a little demonstration of the central limit theorem, which is what we'll be focused on today. So today we're back at the same site to do another demonstration, this one of the central limit theorem. Basically what the central limit theorem does is it tells us that if we have this parent population here and we pull the sample distributions of the sample means, then we're going to see that the means are the same as the population mean. We're also going to see that the variation or the variance is going to change, and the way that the variation is going to change is by the standard deviation is going to decrease by dividing the original standard deviation by the square root of n. And I'll lay all that out for you on some slides in just a minute when we get back to that. But here I wanted to look at the mean with the sample size of 5 and compare that to the mean with a sample size of 25, which is as large as it lets us go. So if I look at this, then what I see is that the mean of this population is the same as the mean of this distribution of means and also this distribution of means. But I also see that the population is much more spread out. When I look at a distribution of means of sample size 5, then it's more condensed and the variation is smaller, so the standard deviation is smaller. And then when I go to a sample size of 25, then that variation gets even smaller. And that's what the central limit theorem is going to talk to us about. Okay, so what is true about the mean of the population and the mean of the sample means? Those are going to be equal to each other. How did the variation of the data change from the population to the sampling distribution? The variation of the data for the population was much larger than it was for the sampling distributions, and the variation got smaller as our sample size got larger. Okay, and this is just another one from that same simulation. If you look at this population, it's all spread out. Our mean would be here. So these means still line up, but you see as the sample size gets larger, the variation gets smaller. So this is section 6.4, specifically talking about the central limit theorem. Okay, so the central limit theorem says that for all samples of the same size n, with n greater than 30, the sampling distribution of x bar can be approximated by a normal distribution with a mean of mu and a standard deviation of sigma divided by the square root of n. So as n gets larger, we can see that the standard deviation of our sampling distribution of sample means is going to get smaller because this value gets smaller as n gets larger. Okay, so we're going to kind of work under the premise that we're working with a population with any distribution that has a mean of mu and a standard deviation of sigma. And simple random samples, all of size n, are selected from the population. So we're just making those assumptions, basically. So what the practical side of this is, if you have a population that has a normal distribution or a large sample, which by large we mean n greater than 30. So if we start out with a population that's normally distributed or n's greater than 30, then we know that our mean of the sample means is equal to the population mean, and we know that the standard deviation of all values of x bar is going to be sigma divided by the square root of n. Okay. If we need to do a z-score conversion, then we're going to have a couple things that change. Our formula for z-scores before looked like this. We're changing a little bit because instead of working with an individual value, we're actually looking at the means of samples. So that's why this x is going to be replaced with an x bar, and the sigma is going to be replaced with a sigma divided by the square root of n. Okay, so if we have a situation where we don't know that the original population is normally distributed, and we also have a sample size that's less than or equal to 30, then basically we're not able to proceed with the methods from this section. Okay, so the first thing when we have a problem like this we want to do is to check our requirements. The two requirements basically are that the original population is normally distributed or the sample size is greater than 30. It has to be one of the two, does not have to be both. Okay, you want to decide if you're working with an individual value or a mean from a sample. So if you're working with an individual value, then you're going to use a z that is x minus mu divided by sigma. If you're working with the mean from a sample, then you're going to have to change your standard deviation to be sigma divided by the square root of n, and your z is going to convert to x bar minus mu divided by sigma over the square root of n. Okay. So as far as our notation here, this mu x sub x bar is the notation for the mean of all the values of x bar. The standard deviation is this sigma with a little subscript x bar, okay? And it's also referred to as the standard error of the mean, and that's denoted as SEM sometimes. Okay, so this is just kind of a chart to summarize it. If our original population is normal, then the distribution of the sample means is normal also. It doesn't matter what sample size it is. If you start out normal for the population, your distribution is normal. If you have one where your original population is not normal, but it's a fairly large sample, larger than 30, then we'll be able to say that the distribution of the sample means is approximately normal. If it's not normally distributed for the original population and the sample is less than or equal to 30, then we're not going to be able to apply the central limit theorem. Okay, so this is just another slide saying the same thing. I'm not going to go back through it. I think we're ready to go ahead and look at some examples here. Okay, so the first example we want to look at, the elevator in a car rental building at San Francisco International Airport has a placard stating that the maximum capacity is 4,000 pounds, which is about 27, and that's for 27 passengers. This converts to a mean passenger weight of 148 pounds when the elevator is full. We will assume a worst case scenario in which the elevator is filled with 27 adult males. I want to say something about that. From a mathematical standpoint, it's considered a worst case scenario because on average, adult males are going to weigh more than adult females. So if we're looking at the maximum capacity of an elevator, in general, the elevator is going to meet its largest load or have its largest load when it's loaded with 27 adult males. Anything less than that, any combination of males and females or even all females would be a situation where the elevator would be filled with a lesser weight load. Okay, we want to assume that adult males have weights that are normally distributed. So this is important with a mean of 189 and a standard deviation of 39 pounds. Okay, so the first thing we want to do is to consider our requirements. The requirements being that it either has to be normally distributed or our sample size has to be greater than 30. So when I look at this, this scenario here, we're told that it's normally distributed. So I'm actually able to check that off and fulfill that requirement. So the next thing we want to do is to decide if it's an individual or if it is a sample that we're working with. Okay. So this one we're talking about one randomly selected adult male. So it's an individual that we're going to be considering. So because it's just one, we're not really going to change how we do this from how we've been doing in section 6.2. I want to find the probability that that one male has a weight that's greater than 148 pounds. So we know that to do this, we're going to sketch this out. Males have a mean weight of 189, so 149 is going to be back here. We want greater than, so it's going to be this part here. So I'm going, since I'm finding a probability, I'm going to do the normal CDF from 149, sorry, this should be 148. From 148 to infinity, which we know we put in the calculator as E99. The mean is 189 and the standard deviation is 39. Okay, so when I put all that in the calculator and round it to 4 decimals, this is the probability that I'm going to get. Okay, moving on to part B. On this one, we want to find the probability that a sample of 27 randomly selected adult males has a mean weight greater than 148. So here we're working with a sample of size 27, and we want to find the probability that the mean weight is greater than 148. So on the previous example, it was an individual, so we represented that with an X. Here it's a sample, the mean of a sample. We're going to represent that as X bar. Okay, so as far as the sketch of it goes, it really is going to look basically the same. The mean is still 189. Standard deviation is 39, and we want the probability that the mean is greater than 148. So as far as how we draw this out, there's nothing different. All right, so we're still going to do a normal CDF. It's still going to go from 148 to infinity. The last two is where the central limit theorem comes into play. The central limit theorem tells us that the mean of the sample means is equal to the population mean. So we need to put the mean of the sample means here, but since they're the same, then we know that that mean is still 189. So for practical purposes, there is no change in the first three things that we identify here. The fourth one is going to change. So we know that the standard deviation of the sample means by the central limit theorem is sigma divided by the square root of n. So if I'm going to put sigma divided by the square root of n, my sigma was identified to be 39 and my sample size was 27. So that's what I need to enter in the calculator. So my answer for that one is 0.99999999765. And I wrote this all out because if I looked at 4 decimal places, it would actually round to 1.0. But if you recall, 1.0 means it's a certain event. So unless it truly is a certain event, we don't like to report it as 1.0. And so that's why I went ahead and wrote all of this out. Okay, so as far as interpretation, there's a 0.8534 probability that an individual male is going to weigh more than 148 pounds, but there's a higher probability given here that 27 randomly selected males will have a mean weight of more than 148 pounds. So here we're looking at the average of 27 males. So based on the results that we have here, if we look at this, it's almost certain that the capacity of the elevator, which is going to be 4,000 pounds, is going to be exceeded if we have 27 adult males on the elevator at a given time. Okay, this is how you would go to StatCrunch to put this in your calculator. I just wanted to show you this because we've already talked a little bit about entering this. For the first one, for part A, you're going to put your mean, your standard deviation, and this is under the normal calculator. And then this, we wanted greater than or equal to the 148, and so this gives us our value here. For the second one, where you have to use the central limit theorem, you actually have to type it in. You have to type in the value itself. So this would be like the 39 divided by the square root of 27. You can either get that decimal answer or you can just type it in as you see here, and it'll register that and give you that probability there. Okay, so all of this is kind of a lead into hypothesis testing, where we're trying to identify if something is a rare event or not. And we've looked at rare events multiple times, so I'm not really going to go into this again. But essentially, if it is a rare event that's occurring, then that's going to allow us to make the assumption, to kind of throw out the assumption that we're working with and believe that something else may be true. Okay, so here's another example that I want us to go through. Assume that the population of human body temperatures has a mean of 98.6. That's basically what it's believed to have been for many years. So also assume that the population standard deviation is 0.62 degrees Fahrenheit. So we have a sample of size 106. It's randomly selected. Find the probability of getting a mean of 98.2 degrees Fahrenheit or lower. So if we look at this, we really don't have anything that tells us it's normally distributed. So if we're looking for our requirements of either being normally distributed or n greater than 30, we don't know that it's normally distributed, but we do have a sample size of 106. So that's going to let that fulfill that requirement there. So we want to find the probability of getting a mean that is 98.2 or lower. Okay, so when we sketch this out with our curve, our mean is 98.6. So here we have 98.2 and lower than that. So we're looking at this. Okay, so I'm going to do the normal CDF, and that's going to be from negative infinity to 98.2, and my mean is 98.6. And because this is a sample, I'm going to do the standard deviation divided by the square root of my sample size. Okay, so the calculator is going to give us this in scientific notation. If you wanted to convert it, you could. Okay, so this is what it would look like. So basically what this is saying is that it is very rare to get a sample of 106 data values that represent the body temperature, and those be less than, the mean be less than 98.2. If in fact 98.6 is the true population mean. So because this is rare for this to happen, and it did in fact happen, then what that kind of tells us is that maybe the actual body temperature is not 98.6. Maybe it's something a little bit less than that. Okay, so this is how we would put this one in our calculator, or not the calculator, in the StatCrunch. So we would have 98.6 for the mean. We put in our standard deviation here, and we want less than or equal to 98.2. So that gives us this probability here. All right, so we talked about kind of interpreting it, but here it's elaborating on it a little bit more. There are two feasible explanations. One is that the population mean really is 98.6 degrees Fahrenheit, and the sample represented a chance event that happened to be extremely rare, but that did occur. The other one is the population mean is actually lower than the assumed value of 98.6, so the sample is typical. And since it is so low, it would be more reasonable to conclude that the population mean is lower than 98.6. All right, so here's one for you to try. So if you would pause it and see how you do with this one. Okay, so on this one here, if you look at it, you're said based on data from the National Health and Nutrition Examination Survey, assume that weights of men are normally distributed. So that is going to fulfill our central limit theorem for us. Has a mean of 172 and a standard deviation of 29. So here we want to find the probability of an individual man that's randomly selected. You want to find the probability that his weight is greater than 175. Okay, so we're going to always sketch these out. So our mean is 172, our standard deviation is 29. We want greater than 175. Okay, so we're finding a probability, so that tells me it's going to be a normal CDF from 175 to infinity. Our mean is 172, and because this is an individual, our standard deviation is going to stay 29. So our value for that is 0.4589. Okay, moving on to part B. Same information, it still fulfills the central limit theorem. This time we want the probability that 20 randomly selected men will have a mean weight that's greater than 175. So we want the probability that they have a mean weight, so we're going to use X bar here, greater than 175. So my sketch will look the same as it did before. So it's going to look like this. So I'm going to do the normal CDF from 175 to infinity. My mean stays the same. My standard deviation for this is going to be the standard deviation that's given to us for the population divided by the square root of my sample size. My sample size was 20. Okay, so when I put that in the calculator, I'm going to get 0.3218. Okay, and this is how, if you were doing it on StatCrunch, it would look. Okay, so we have these two probabilities given, and the question is which is more likely. When you're asked which is more likely just simply means a larger probability. So don't try to rationalize it in your own mind. We've kind of relegated it to simply being a comparison of these two probabilities. Since this is a higher probability, then it's more likely that one man is going to weigh more than 175 pounds than it is that 20 men will have a mean weight more than 175 pounds. Okay, here's another one for you to try. Okay, so for this first one, the average teacher salary in North Dakota is $35,441. Assume that we have a normal distribution, so therefore we can satisfy our central limit theorem, and we have a population standard deviation of $5,100. What's the probability that a randomly selected teacher salary is greater than 45,000? So it's saying A, so that's an individual. Right, so if we looked at the sketch here, the mean is 35,441, and we want to know the probability that it's more than 45,000. So I'm going to do the normal CDF from 45,000 to infinity. Our mean is 35,441, and our standard deviation is 5,100. We don't need to divide by anything because it's an individual. So that probability is 0.0304. Okay, for part B, for a sample of 75 teachers, so that one tells me that I've got to use the central limit theorem. What's the probability that a sample mean is greater than 38,000? So our mean is 35,441. We want to know the probability that it's greater than 38,000. So we're going to do our normal CDF because it's a probability that we're looking for. 38,000 to infinity. Our mean is 35,441, and our standard deviation is 5,100 divided by the square root of our sample size. So that's going to be the square root of 75. So that is 0.00006956. So on occasion, you may see this reported as 0 plus. So that is acceptable so long as you have the work to back it up. You may also see this as 0.0001. And it takes a little bit of explaining to understand how that is what we would report as our answer. If you're only allowed to report 4 decimal places, this is the smallest number that you can report, 0.0001. So if we did anything smaller than that, it would be 0, and 0 would be an impossible event. Well, this is not impossible. I mean, for all practical purposes, it is fairly impossible, but it's not statistically impossible. So because it's not statistically impossible, we wouldn't report it as just a pure 0. So we could do 0 plus, like I said, or we can do it like this, but those are really the only two options. So we're not saying that this rounds to this. We're just saying that if we're limited to only give 4 decimal places, then this is the smallest 4 decimal place number that we can give, and therefore that's what we have to give as our answer. Okay, moving on to look at this problem here. You're asked to obtain new desks for an incoming class of 25 kindergarten students who are all 5 years of age. So let's assume that you are a principal at an elementary school and you're needing to make this decision. So an important characteristic of the desk is that they must accommodate the sitting heights of those students. The sitting height is the height of a seated student from the bottom of the feet to the top of the knee. And then the table lists the parameters for sitting heights of 5-year-old children. So we want to know what sitting height will accommodate 95% of the boys. Okay, so if we look at this, if we're working with just the boys, we know that both of these are normally distributed, so that's not an issue. So if we want to accommodate 95% of the boys, we're asked to find a height. So if I'm trying to find a height, that's a value that I have to find, and therefore I'm going to be doing an inverse norm problem for this. So if I want to accommodate 95% of the boys, I want you to think about if you were to sit in a seat, would you be better accommodated if your feet were too short and didn't touch the ground? Or if you were like an adult trying to sit in a kindergarten chair and your legs were like kind of thrown out to the side and you weren't able to actually sit in the chair. I think you'd be convinced that it's a better fit if your feet don't hit the floor than it is to have your legs being too long. So what we want to do is it's okay for people to be shorter. We just don't want to have people that are a lot taller than this value. So we want to accommodate 95%, and this would be the 95% that we're going to accommodate. So only about 5% would be taller than this value, and therefore only about 5% would be sitting uncomfortably in the chair. All right, so this is a value that we need to find, and this is an X because it's not standard normal, so it's going to be an X. So since I'm finding a height, I'm going to do the inverse norm. The area to the left of this is 0.95. The mean for boys is 61.8 and the standard deviation is 2.9. So I'm not going to divide this by anything because there's no mention of a sample size. So we're just going to take this as an individual and come up with this value. Okay, moving on to part B. What sitting height is greater than 95% of the means of sitting heights from random samples of 25 boys? Okay, so same idea, except this one is going to use the central limit theorem because we have a sample of, so we have a sample of 25. So we want to find the height that's going to accommodate that. So we're going to go in and find the sitting height that's greater than 95% of the means of sitting heights from random samples of 25 boys. So we're trying to still find this, except we want to find the sitting height here, the average. So we're going to do the inverse norm of 0.95. Our mean for boys is 61.8. And here, because we're talking about a sample of 25, our standard deviation is going to be 2.9 divided by the square root of the sample size, so divided by the square root of 25. Okay, part C, based on the preceding results, what single value should be the minimum sitting height accommodated by the desk? Okay, so you're the principal, you've got this information, you've got to figure out, are you going to buy a desk that for part A was 66.6 inches and that was specifically for an individual, Or are you going to do the one for the group, which was 62.8? And in this case, that was centimeters, not inches. And that was for a sample of 25. Okay. So if you look at these, the natural tendency is to say, like, okay, we want to buy for the average person, so 62.8 centimeters would be what we would want to buy. But if you think about it, we already said that in order to accommodate 95% of the boys, we'd have to have a desk with a sitting height that's at least 66.6. So if I'm cutting it back and getting one that's 62.8, then I'm not going to be accommodating 95% of the boys. I'm going to be accommodating something significantly less than that. So generally speaking, when you have something, whether it's a seat, a helmet, a seat on an airplane, anything like that that is used by an individual, then we need to be more concerned about the individuals than we are the collective average of a group. The other part of this, why are the sitting heights of girls not included in the calculations? So you can see that the girls are have a mean that's less than the boys. So if the boys are being accommodated, then basically by default, we're going to be accommodating at least 95%, if not more, of the girls as well. Okay, and so this is just what the work on StatCrunch would look like for these. Okay, here's one I would like for you to take a few minutes to try, and this one really does kind of lead into hypothesis testing, which will come up in Chapter 8. Okay, cans of regular Coke are labeled to indicate that they contain 12 ounces. So we're going to assume that we have 12 ounces in a can. So we take a sample, and the statistics from the sample are as follows. So we have a sample size of 36, and from that sample, the sample mean is 12.19 ounces. So if the Coke cans are filled so that the mean is 12 ounces, as is printed on the label, and the population standard deviation is 0.11 ounce based on sample results, find the probability that a sample of 36 cans will have a mean of 12.9 or greater. So what we're finding is the probability that the mean is greater than 12.19. Okay, so we are going to have to use the central limit theorem. So I need to either know it's normally distributed or n's greater than 30. Well, our sample size is 36, so I automatically know that one, and so I'm good to use this. If I look at the graph here, my mean is 12. So we've got 12.19. So I'm going to do the normal CDF from 12.19 to infinity with a mean of 12 and a standard deviation of 0.11 divided by the square root of 36 for the sample size. Okay, when I get that value, I'm going to see that it is 1.86 times 10 to the negative 25th. I'm not even going to try to write that out, but I think we can see that that is very, 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 very small. Okay, so what that tells me is if it's true that cans have 12 ounces in them, then it is almost impossible to select a sample of size 36 and have the mean be 12.19. Okay, so I have two scenarios to explain this. One is that we picked that very rare event where we did get the one sample that had a mean of 12.19, even though it was very, very unlikely that that would happen. We just happened to get lucky and get the one that did. Or a more reasonable explanation is that, in fact, our assumption is not true and that maybe each can actually has a little bit more than 12 ounces in it, so that when we take this sample, we get a mean that's a little bit higher than 12. Okay, here's our last example for today. So go ahead and try this. We're going to take it kind of in parts. Okay, on the first one here, it's really not asking a lot of statistics. Okay, it says given that the gondola is rated for a load limit of 3,750 pounds, what's the maximum mean weight of the passengers if the gondola is filled to the stated capacity of 25 passengers? So in other words, if we're going to be right at the load limit of 3,750 pounds and there's 25 passengers on there, then what can each one average to put it at its maximum weight? So I'm going to take the 3750 and divide it by the 27 passengers. So I get 150 pounds. So on average, the average person can weigh 150 pounds, and that's going to put us right at that maximum weight limit. If people weigh more than 150 pounds, then we're going to exceed that maximum weight limit. Okay, part B. If the gondola is filled with 25 randomly selected skiers, what's the probability that their mean weight exceeds the value from part A? So if we look at this, our value from part A was the 150 pounds. So we want the probability that their mean weight exceeds 150 pounds. Because if their mean weight exceeds 150 pounds, then their total weight is going to exceed the load limit here that we're talking about. So we already know that the mean is, see, the mean was 201 pounds and our standard deviation was 35 pounds. So this is going to be, I'm finding a probability, so it's going to be the normal CDF from 150 to infinity, and I always like to have it sketched out here. I just forgot to do that. So here I'm at 201, 150 is back here, so I'm finding this probability here. So 150 to infinity, I have a mean of 201, standard deviation of 35. I'm going to divide that by the square root of 25. Okay, so we get a mean of 1, which statistically speaking means it is a certain event that if we have these descriptive statistics provided here, we're going to have an average that's more than 150 pounds. Okay, part C. If the weight assumptions were revised so that the new capacity became 20 pounds and the gondola is filled with 20 randomly selected skiers, what's the probability that their mean weight exceeds 187.5 pounds, which is the maximum mean weight that does not cause the total load to exceed 3750? So I want the probability that their mean weight exceeds 187.5. So we're looking at a graph that looks like this. Our mean is 201 and so 187.5 is back here. We want it to be greater than, so it's going to be this part. So I'm going to do the normal CDF from 187.5 to infinity, which is E99. Mean is 201, and here our standard deviation is 35, and we're going to divide that by the square root of 20. Okay, so if we look at this one, we see that the probability that it's going to exceed the 187.5 pounds is about 0.9577. So about 95% of the time, it's still going to be exceeding a safe capacity. So is a new capacity of 20 passengers safe? In most cases, it's not going to be safe because it is going to be exceeding this the weight capacity, and therefore it probably needs to be lowered even lower. Okay, for the first one here, you're finding a probability. Okay, so the average age of a vehicle registered in the U.S. is 8 years or 96 months. Assume that the standard deviation is 16 months. If a random sample of 36 vehicles is selected, find the probability that the mean of their age is between 90 and 100 months. So I'm going to write that as 90 to 100, and again I'm going to use X bar for that. So when I sketch this one out, my mean is going to be here at 96. So I'm going to go from 90 to 100. I'm looking for this probability in here. So this is going to be a normal CDF because it's a probability problem. From 90 to 100, the mean is 96. Standard deviation is 16. So I get 0.2449. Okay, the next one, the average number of pounds of meat that a person consumes per year is 218.4 pounds. Assume that the standard deviation is 25 and that it's approximately normally distributed. So looking at this for our central limit theorem, we know it's normally distributed, so we're good with that. For part A, this one's an individual person. We want the probability that a random person consumes less than 224 pounds. So if I sketch this out, my mean is 218.4. So I want 224. So that's going to be this part here. So it's a probability. So I'm going to do the normal CDF from negative infinity to 224. Mean is 218.4 and the standard deviation is 25. Okay, so that value is the 0.5886 that you see here. The next one, we want a sample of 40 individuals to be selected. Find the probability that the mean is less than 224. So this one, we're going to have x bar is less than 224. So that's going to be a normal CDF of negative infinity to 224 with a mean of 218.4, and our standard deviation on this one is going to be 25. Divided by the square root of our sample size. Our sample size is 40. Okay, so I get 0.9217 for my answer. Okay, if you have any questions about any of the Chapter 6 material, please be sure that you're joining us for the Zoom sessions and also for office hours. So make sure that you get your questions answered, that you don't let them go unanswered, because that's going to hinder your understanding of the next chapters as well. Thank you and have a good day.